Hello friends, welcome to my channel once again. Today we are going to explore the concept of relativity. As we hear this term, the first picture we conceive in our mind is of the Albert Einstein and his theory of relativities, namely special theory of relativity, which was represented by him in 1905. Later on, he reconciled it with the concept of gravitation and it was presented in 1915. The well-known equation E equal to mc square is again from the special theory of relativity, and general theory of relativity presents us the set of 10 differential equations, which is here represented by this single expression, where these terms represent the space-time, which is a unique concept given by him in the special theory of relativity, and again this was reconciled in the general theory of relativity. Then there is a story about cosmological constant, which I put here as lambda in the red color. So we will look at what the fuss is all about, what is the anxiety in the curious people about all this time dilation, time traveling, all those things, but not today, because on the face value we all know these concepts are incomprehensible. So what we are going to do is, today we are going to take the concept of relativity by another genius luminary, that he was Sir Isaac Newton. So there is a very unique concept of relativity from him also, although it is not as famous and popular like we have with the Albert Einstein. So let's explore what it is. The first thing is, let's say this is a graphical representation. It is the x-axis, this is the y-axis. I hope you all know this basic concepts, right? And then there is a red box you can see here. This red box is representing a train moving at some uniform speed. Now I hope you all know the uniform speed concept, and that speed is, mathematically we can write it as v equal to s by t. S is the displacement or distance, because we are not going to see very seriously about the direction, scalar and vector concept, right? So you can simply say as v is speed or velocity, s is displacement or distance, and t is obviously the time, right? So let's say our train is moving with a uniform velocity or uniform speed. That means its speed is not going to vary with respect of time, right? So when it is moving and there are passengers inside the train, right, and there are people outside the train waiting for it, right? So now, can we say that these people inside the train are at rest or motion? Now, here comes the first breakthrough about the relativity, right? Now, you see, both persons are sitting in their respective seats on the train. So, for each person, the other person is stationary, is at the rest, right? But for a person outside the train on the platform, for him these persons are in motion. So what we understand is that motion or rest is a relative thing. It depends upon the observer. When we talk about relativity, obviously that means we are talking in respect to some observer. Then there comes the concept of inertial frame of reference, non-inertial frame of reference. These concepts are very, very important to understand the special theory of relativity or general theory of relativity. But without going into that much, right, here we will concentrate how this shows us something unique about relativity, and that is that space is relative. What do we mean by space is relative? That means for one observer, right, there is, if you measure the space, right, for one observer it may be different, and for other observer it might be different, right? So that is, I say here is the space is relativity. And how we understand this, let's see. So as one passenger throws a ball inside the train and catches it, right? So let's say so if you make a graph, right, for this train, so he throws a ball and he catches it again, that means what is the change in the position of a ball? It is 0, because from the point where it was thrown, at the same point he catches the ball, right? So that means there is no shift in the x-axis, although the ball traveled some distance in the y-axis, but there is certainly no change in the x-axis. But if the observer outside the train measures how much distance ball traveled in the x-axis, so seriously the ball traveled, right? Let's say assume some mathematical data, right? So the speed of the train is, let's say, 1 meter per second. That is, train is traveling 1 meter of distance in 1 second. So when you throw the ball inside the train, right, let's say it was at the position 5, right, for the outside person, right? Now after 1 second, right, this position changed to 0.6. When it changed to 0.6 and the ball was caught, so it was at the 0.6, right? So for one observer, this green observer inside the train, for him there is certainly no space, right? Space between what? Space between the point from where it was thrown and the point where it was caught, right? There is no space between these 2 points. But for the observer outside the train, what he observes? He observes that there is a space, there is a gap of 1 meter between these 2 points. Which 2 points? The point from where the ball was thrown and the point at where the ball is caught, right? So now what is the truth? Can we say that this person, green person, is right and black person is wrong, or black person is right or green person is wrong? No, both are right at their position, right? And this concept is called as relativity. And what we understood is that space is a relative thing. So in the previous video we understood about the space, and how we understood is that space is a gap, right? Now, so what here we understood is, for two observers at two different conditions, right? For one observer there is no space at all. For the other observer there might be a huge space. I hope you understand this and enjoyed it. If you want more videos related to such concepts, such interesting concepts and informative concepts, so do subscribe my channel, like it, share it and comment. So thank you for watching it.